A warm greetings to one and all. In this session, let's learn about uniform cost search algorithm with an example. It is a graph search algorithm used to find the shortest path from a starting node to a goal node. It operates by expanding the least cost node first and ensuring an optimal solution in terms of path cost. Key features are it uses the priority queue to select the node with the lowest cost. It always expands the cheapest node first. It ensures the optimal path if all edge costs are non-negative. It is similar to Dijistra's algorithm, but it focuses on goal-directed search. For UCS, the function used to expand the node is f of n is equal to g of n, where g of n is the actual cost from the start node to the node n, that is the current node. UCS is widely used in applications like route planning, AI decision making, robotic navigation, where we need to find the lowest cost path is very essential. Now let's learn about the algorithm for uniform cost search. The first step is initialization. So here we need to create an open list with priority queue and we have to add the start node with cost 0. Next we have to create the closed list to track the visited nodes. The step 2 is loop until the open list is empty. That is, we need to select the node with the lowest cost from the open list. So next we have to move it to the closed list. If it is the goal node, then we have to stop the search. In step 3, we need to expand the selected node. So we need to add its unvisited neighbors to the open list with updated cost. If neighbor is already in the open list with a higher cost, then we need to update it with the lower cost. The final step is to repeat step 2 and 3 until the goal node is reached or the open list becomes empty. Now let's solve an example problem for uniform cost search algorithm. Let's consider this problem where the start node is A and the goal node is G. Now let's start the search algorithm from node A. The same must be updated in the table. In this table, we have open list, that is, we have node along with this cost, and we have closed list, which represents the expanded node. In step 1, we have opened the node A with cost 0 since it is the starting node. As of now, we didn't expand any nodes, so the closed list is none. In step 2, we need to expand the node A. So now we need to find its neighbors. That is, from A, we have the neighbors as B and C. The cost required to reach B from A is 5, and similarly, the cost required to reach C is 9. The same can be updated in this tree. So A to B is 5 and A to C is 9. So we need to update the same in our table as B, 5 and C, 9. That is, from A to B, the cost required is 5 and from A to C, the cost required is 9. Since node A is expanded, now it can be moved to the expanded node, that is closed list. Since we are using priority queue, the neighbor nodes which are added to the open list are always in ascending order based on the cost. In step 3, we need to expand the node B, since node B has the lowest cost value. Now let's check out the neighbor nodes for node B. The neighbor nodes are A, B, and E. Since we have expanded the node A, we can skip it and we can choose the node D and E for further expansion. So the cost required to reach D from B is 2 and the cost required to reach E from B is 8. The same can be updated in R3. So already the cost of node B is 5. In addition to that, if we move to the node D, we have the cost 2. So 5 plus 2 is 7. From B to E, already we have the cost for node B is 5. Now we have to add the value 8 along with it. So 5 plus 8 is 13. So the same can be updated in our table. That is, the neighbor nodes are added to the open list in ascending order based on its cost. Since we have expanded the node B, it has been updated in the closed list. In step 4, we need to expand the node D since it has the lowest value in the open list. The neighboring nodes of node D are node B, node E, and node G. Since we have already expanded the node B, we can skip it and we can consider node E and node G. In order to reach the node G from node D, the cost required is 6. Similarly, in order to reach node E from node D is 7. The same can be updated in our tree. The cost of node D is 7. If we expand it from node D to node G, that is 6 plus 7 is 13. Similarly, if we expand the node D to E, the cost is 7 plus 7. That is, already we have cost 7 for node D, and to reach E from D, the cost is 7. So 7 plus 7 is 14. The same can be updated in our table, where the neighboring nodes G and E are added to the open list in ascending order based on the cost. Now we can move this node D to the closed list since it has been expanded. In step 5, we need to expand the node C since it has the lowest value in the open list. The neighboring nodes of node C are node A and node G. Since we have already expanded the node A, we no need to consider it. We can consider the node G. The cost required to reach the goal node G from node C is 12. So we can update the same in our tree. Already the node C has the value 9. If we expand it to node G, the cost required is 12. Therefore, 9 plus 12 is 21. Already in our open list, we have the goal node G with cost 13. This is the lowest cost. So we can skip the currently generated node G, and therefore there is no updation in the open list. We can move node C to the closed list since we have expanded it. In step 6, we need to expand the node E with the lowest cost 30. The neighboring nodes of node E are node B and node D. Both the nodes were already expanded and placed in closed list. So we can skip this node expansion. However, if we expand this node, sure we may require more cost to reach the goal node. Since already we have reached the goal node at cost 13 in earlier step. So we can skip this node expansion. The same is applicable for the node with cost 14. So we can skip this node expansion also. Now we have only the node G with cost 13, and that is the goal node which we need to reach in the open list. Since we have expanded the node E, we can move it to the closed list. Finally, we have reached the goal node G with the lowest cost 13 in the open list, and we have visited all the nodes, namely A, B, C, D, and E, and placed in the closed list. The final solution of our problem is the optimal path required is A to B, B to D, and D to G. We can see here in our tree, that is starting from A, we have moved to B, B to D, and D to G. The total cost incurred to reach the goal node is 13. So hope you are clear on uniform cost search algorithm with this example problem. Properties of uniform cost search is evaluated by 4 of the following factors. The first one is completeness. It is complete if branching factor B is finite always. The time complexity of uniform cost search is exponential, that is order of B of 1 plus C divided by epsilon, because every node is checked here. Space completeness is also exponential, that is order of B of 1 plus C by epsilon, because all the nodes are added to the list of comparisons of priority. Finally, optimality. UCS gives the optimal solution or path to the goal node always. So hope you are clear in uniform cost search. Thank you all.